Good afternoon. Okay, today I'm going to present one of the work that have been done during my PhD thesis. So the work is entitled Using High Resolution Thermometer Data for with a Constrained Thermal Based Energy Balance Model, which we named TESAB-SM over our field. So first, let's outline the context of our study. As we all know that the human survival depends on clean water, and the human being is facing a serious crisis because of the shortage of water. And this is impacted by the population growth, the increase of demand, and overexploitation of the water resources by agriculture. Also, there is an impact of climate change, as we all know, and distribution of precipitation, and also the increase of temperature. And this is a major problem for semi-arid and arid areas. And this problem will continue to progress if not an adaptive action should be made. And one of the well-known initiatives is the adaptation of African agriculture to climate change, which has many objectives: soil management, agricultural water control, and climate risk management. So the solution is using smart agriculture to ensure at the same time the water and food security. Okay, and one of the key monitoring variables for the water consumption is the evapotranspiration, as it is responsible for dissipation of around 60% of the rainfall. And the evapotranspiration is impacted by climate demand, vegetation, and also by groundwater. So what we propose, or all research that's working on this thematic, propose the partitioning of evapotranspiration into evaporation and transpiration to optimize the water management practices and irrigation regimes. So there is a lot of instruments or many models that are used to estimate the evapotranspiration model, but what we propose is the synergy between the trio: remote sensing, process modeling, and also in situ measurements. Okay, I'm going to start by the model that we are using for this study. So the model is mainly developed by Norman, which is the TESAB model. And we added an additional constraint, which is soil moisture, to better estimate the soil evaporation. So for the TESAB, the classic TESAB model, we estimate the soil evaporation as a residual term of energy balance. But we propose to use this equation to estimate the soil evaporation, and we will propose an innovative approach to calibrate the two parameters: the LSS, which is a soil resistance, and the alpha PT, which is the coefficient of precipitator model. So the approach is like for the fractional cover inferior to a fractional cover threshold. It is especially 0.5 or 0.4. It depends on the crop we are working on. So we suppose that the evapotranspiration is mainly controlled by soil evaporation. So we don't have a transpiration. What we did is we inverted an instantaneous resistance by minimizing the cost function between the land surface temperature simulated by the model and the land surface temperature that we measured by the instruments in the field or by remote sensing. And the second step, we suppose that the process of evapotranspiration is mainly controlled by the land transpiration. So we don't have a soil evaporation, as the soil is mainly covered by vegetation.
I don't see the screen on that. The screens are shared. What do they say?
Can you see the screen now?
No, still we're seeing the presenter's view.
Yes, actually, we can see now the screen.
Okay, thank you. So I will continue the presentation as we don't have enough time to repeat from the beginning. So we arrive to the second step of our calibration model. So as I said, we suppose that the process of evapotranspiration is controlled by transpiration as the soil is fully covered by vegetation. What we do is we invert a daily basis precipitator coefficient by minimizing the cost function between land surface temperature measured and simulated by the model. So our approach has been applied over several wet fields in intensive basin. I will just present some of the results that we got over Shishawa, which is an irrigated area by drip. And here we have two parcels. One irrigated by the farmer according to the FAO recommendations, and the second which is provoked by stress during growing season. And the second parcel, it is located in Archi, which is an area far from Marrakesh, about 40 kilometers, and it is done or was maintained in 2002-2003. Okay, here I'm presenting the result of the calibration. As we can see that the two parameters that used to estimate the soil resistance are converged, the model converged like fast after 2 or 3 iterations. And the average values are 7.2 and 4 for and BL6. And those questions are quite similar to those are found in literature. And the average of the precipitator coefficient is close to the theoretical value, which is 1.26 for the field, for the reference field in Shishawa. Why? Because this site is well irrigated according to the required estimated irrigation by the FAO 56. Here I'm presenting the result of the inverted precipitator at the daily basis. So the maximum is around 1.45, 1.89, and 2.82 for the archery control, and then reference parcels. So what we did, like to reduce the fluctuations, to remove the outliers, and also to keep a significant variation on a quasi-daily scale, we apply a smoothing function. And as you can see for the archery, when we smooth the variation of precipitator, there is like a small variation of the signal of alpha PT, because we can see the difference between the maximum of the precipitator coefficient between the sites in Shishawa and also in Archi, because there is a big difference between the agricultural practices, especially the sowing date, irrigation and fertilization that we applied for those sites. Here what we did, like we normalized the precipitator coefficient between the maximum value and 0, because we suppose that in the senescence period we don't have transpiration, so the alpha PT coefficient should be equal to 0. So as I explained before, the alpha PT is more stable for the reference field, and there is a big variation for the archery and for the controlled parcel in Shishawa. So we're gonna go more in detail for these variations. So we plot this variation with the soil moisture at 5 centimeters, and the soil moisture at the root zone, which is around 30 centimeters, and the data of vegetation water content. So we can see that the dynamic of the alpha PT depends on the variation in soil moisture in the surface and also in the root zone. And the maximum of the coefficient values follow the variation of the vegetation water content. So what we see also that during stress, there is a decrease of the coefficient, because sometimes there is an increase in water depletion in the root zone, or there is a problem of water loss through transpiration or through perforation, as justified by in a paper of Salah. Okay, here we arrive to the results of this variation of alpha PT and the soil resistance that we calibrated on turbulent fluxes. We start by the sensible heat flux. We see a significant improvement of the results of TSEB compared to the classical TSEB because of the improvement we did in the soil resistance and on alpha PT coefficient. And also for the latent heat flux, we can see that there is a big improvement of the latent heat flux or evapotranspiration, because especially in the senescence period, because for the TSEB, the classical TSEB, they suppose that the alpha PT is always 1.26, which is not the case. It is a coefficient that decreases with time and equal to 0 at the end of the senescence. Okay. To test the applicability of our model at large scale, we used the soil moisture from satellite data, and in this work we tested several soil moisture from different sources. So the first soil moisture was retrieved by Sentinel-1 and just by Sentinel-1, which is the approach developed by NENA. And the second approach, it is the TEA soil moisture, where we use the machine learning algorithm and Sentinel-1 and Sentinel-2 to retrieve soil moisture. And the third one, which is a smooth data disaggregated to 100 meters. So we use those data to feed our model and to see if we can get an accurate estimation of evapotranspiration. I didn't present the results that we for the validation of each site, but I present the maps that we get over the R3 irrigated area, which is mainly it is mainly covered by weeds. Okay, we arrive to the conclusion. So there is a clearly improvement in terms of evapotranspiration, because we constrain the model by soil moisture to improve evaporation, and we calibrate the Priestley-Tyler coefficient, and this improves the transpiration, especially on growing and senescence period. And also we see that this approach is applicable at large scale while using remote sensing soil moisture. Each model has its limitation, and the limitation for the TSEB model is the resistance used to estimate evapotranspiration, especially the soil resistance, that is influenced by soil texture and structure, and also this is the soil resistance at 5 centimeters, and the surface soil moisture surface resistance. It is difficult to characterize because it is affected by the wind speed, the roughness, and also the canopy type. And also the problem of using soil moisture at high resolution. We found just few data that are in the same overpass with the land surface temperature. There is always like 2 days and 3 days of difference between the overpass of satellite for soil motion and for land surface temperature. If you need like more explanation about the model and the result we got, there is many papers that have been published about this model. Thank you for your attention. I will move on to the next presentation. Salah, Dr. Salah is not with us, but I will present in his place. Okay, I will go into the objective of the study. So the objective is development of a methodology for the evapotranspiration characterization and to contribute to development of decision-making tools dedicated to water resources management. And the specific objectives of this study is measurement of turbulent fluxes in the high atlas pavement using the centrometer and the electrocurrent system, the performance and validity domains of evapotranspiration modeling tools, and demonstrating the potential of remote sensing data while using high spatial resolution of natural gas temperature for estimating ET in the pavement.
We don't have the presentation on the system.
Okay.
Such
Dr. Salah Rocky, she now presenting on behalf of Dr. Salah.
yeah, still the presentation is not on Teams.
Here presentation.
This one is not shared. Can you share it?
Okay.
Okay. And now? Can you see the screen?
Yes, for us, I think it's clear. We can see the
Objectives.
Okay. Nice.
Okay. Okay, I will move on to the study site. It is an area located 30 kilometers south Marrakech city. It is an area covered by heterogeneous land cover, especially olive trees, fruits, and wheat. And for the height, there is differences in height, especially for the olive trees. There is the height that varies from 2 meters to 13 meters. And the system of irrigation adapted here is the irrigation by flood using the system of Sevilla. So the parcels that are located.
That's the thing they are seeing. This thing that they're not seeing the sites.
Yes, we are still on the first one. So maybe you're not sharing the right presentation.
What I should do is.
Sure.
Okay.
No?
Yes.
Okay. I will move on to the system of irrigation. So as we are in the pavement area, the irrigation depends on the location of the parcel and also the size of the parcel. So the parcels that are located in the upstream are those who benefit from the irrigation first. And those who are located in the downstream, they are the final users of or beneficiaries of irrigation. And during dry seasons, those parts that are located in the downstream, they just pump water to irrigate their parcels because the water doesn't reach their parcels. Okay, in this pavement, we installed 2 ED covering systems. One over olive trees and the other over an heterogeneous parcel, which is EC2. There is fruits, olive trees, and also wheat on this parcel. And we installed a large aperture centimeter that covers a transect of 1.4 kilometers. And covering like the whole pavement area. Here it is like an illustration of the footprint of the measurements for the electro-ovarian system and for the centrometer. This footprint, as you all know, is affected by many factors, especially the measurement height, the atmospheric stability, and the wind speed and direction. There is
connection problem.
Is it here?
We don't see the presentation changing.
هو فين